morning, everyone. It's my pleasure to start the first session of today's nice meeting on natural sciences. The good news is that we are 7 minutes earlier, according to schedule, so this is good. So we have more time for questions. So I guess let's start with the first talk, which will be Kaloyan Lozanov, University of Cambridge, who is going to talk about nonlinear dynamics in the other universe. We have 10 minutes for the presentation and 5 minutes for questions afterwards. We'll try to stick to schedule, although of course if it's very interesting we can allow a little bit of flexibility.
Okay, thank you very much. Okay, so my name is Kaloyan Lozanov. I'm a second year PhD student in the University of Cambridge. I'm doing a PhD in theoretical cosmology in the Institute of Astronomy under the supervision of under the supervision of Dr. Mustafa and Dr. Chalino. And today I'll outline the two projects that I've been working on recently. The two projects consider different aspects of objects which might have formed during the earlier stages of the evolution of our universe. These objects are described by nonlinear dynamics, which makes them interesting but also really difficult to study. But before I get into the projects, let me make a brief review of the history of the universe so that I can put our work into context. So we know that the first nuclei were formed when the universe was 38 masses ago, and then as this hot and filled with very dense and filled with particles universe expanded, eventually the cosmic microwave background was emitted when the universe was 40,000 years old, and then the first stars came about, the first galaxies. This picture of the universe, this model of the universe is broadly accepted and is known as the hot Big Bang. Why hot? Well, because the universe began expanding from a very hot state. And the hot Big Bang is one of the successes of the 20th century theoretical cosmology. However, there is one problem, and the problem is that the cosmic microwave background radiation, which we observe today, the so-called CMB, is too homogeneous, and there is no way of accounting for this homogeneity within the framework of the hot Big Bang. So we need an extra ingredient, and this extra ingredient comes in the form of inflation. So what is inflationary cosmology all about? Well, inflationary cosmology assumes that the universe underwent a very short but very rapid period of expanding. During the first, or you can't see it very well, but during the first minute fractions of the second of its existence. And inflation provides us with a mechanism for generating the homogeneous CMB, or as homogeneous as we observe it today. And inflation is considered as another success of the 20th century theoretical cosmology. However, inflation leaves us with another problem. And the problem is the following. How do we connect inflation to nucleosynthesis? And the connection is not straightforward because during nucleosynthesis, or at the beginning of nucleosynthesis, the universe is really hot and filled with particles. Whereas at the end of inflation, the universe is cold and virtually empty of particles. And there isn't a straightforward way of connecting these two states. And the process which takes us across this gap is known as reheating. And essentially, reheating is the main topic of my PhD. Reheating is a very important stage of the evolution of our universe. As you said, because it connects the inflationary universe, the empty, the cold universe, to the cold thermal universe. At the main nucleosynthesis, reheating virtually explains the origin of the elementary particles that we observe today, because during reheating, the universe got populated with particles for the very first time. And reheating is also really important because it is dynamically rich. You can get various energetic phenomena in the way of explosive particle productions, etc. And you can also form very interesting objects, such as oscillons. And oscillons were the topic of the two projects that I've been working on recently. You can think of oscillons as localized lumps of energy, which are very stable, which live for very long times. And if they formed during preheating, they might have dominated the energy budget of the universe for very long times. And that's why people believe that they're really important for heating and relevant to the evolution of our universe. And the aim of our first project was to investigate how the formation of these hypothetical objects, oscillons, might have affected baryogenesis. Baryogenesis is the process which explains the generation of the asymmetry between baryon matter and baryon antimatter. Essentially, the asymmetry between the matter and antimatter that we observe today. And in order to test how oscillons might have affected a certain class of baryogenesis models, we took a generic class of baryogenesis models off the shelf, whose main idea was the following. The inflaton field, which is the field which drives inflation, is assumed to be complex. I'm sorry that this slide is a bit technical, but just please bear with me. So in this model, the inflaton is assumed to be a complex scalar field. This way we can assign both particles and antiparticles to the inflaton field. Then the potential of the inflaton field is slightly modified so that the dynamics during preheating generate an asymmetry between the number of inflaton and anti-inflaton particles, and eventually this asymmetry is transferred to the matter-antimatter asymmetry, which we observe today through decays of the inflaton field to ordinary matter. So this is the general idea of this very generic baryogenesis model. And in our first work, we include oscillons into this framework by modifying the potential of the inflaton field so that it will give us oscillons. And then we essentially investigate what happens with the asymmetry. We discover that the asymmetry is changed significantly in various ways. And one of the interesting results which we discover is essentially the answer of the question which hasn't come up really cleanly. But basically we discovered that the asymmetry, when oscillons are formed, ends up locked inside these oscillons for very long times. So we discovered that the asymmetry ends up locked inside the oscillons, and this might leave us with potentially observable signals, and we might be able to observe them in the future, where we did not pursue this idea further. We called it Sunmodel. Instead, we moved on to our second project, which considers what happens with oscillons in more realistic models when they are coupled to other forms of matter. For example, electromagnetic fields. Here, inner gauge fields is the colloquial term for electromagnetic fields, essentially. And basically, in this project, we try to answer the question: are oscillons formed during preheating, long-lived when they are coupled to other forms of matter? And well, here the questions don't come out, but they are not important. The idea is that they're too technical. But the main challenge of this project was that simulating a universe in which oscillons are coupled to magnetic fields cannot be done with the available tools on the market. There aren't codes which can perform simulations of an expanding universe with oscillons and magnetic fields interacting. And I spent the last several months developing such a tool. And here I can show you my preliminary results. So on the left-hand side you can see oscillons which are coupled very weakly to electromagnetic fields, and the simulations tell us essentially that oscillons survive. They do not decay away when they're weakly coupled to electromagnetic fields. So you can see how oscillons initially form, and then they non-decaying. Whereas on the right-hand side, when osteons are coupled, I'm really sorry that the slides are not very clear, but on the right-hand side you can see again the box of our simulation in which osteons decay when they're coupled more strongly to electromagnetic fields. And this is something interesting, simply because people normally believe that osteons are long-lived and they remain long-lived even when they're coupled to ordinary matter fields, whereas here we discover that they might stabilize provided they're coupled to electromagnetic fields. Not only this, we also discover that here I'm plotting the equation of state of the universe. But the important message to take away from here is that the equation of state of the universe, when osteons are coupled strongly to electromagnetic fields, reaches very quickly the equation of state of the universe, which is dominated by radiation. And this is one of the conditions required for the end of reheating. So we see that when osteons decay to electromagnetic fields, we can attain a very efficient way of reheating the universe, a novel and very efficient mechanism for reheating the universe. Yes, and let me wrap it up. So, as I said, reheating is an integral part of inflation cosmology. If you believe in inflation, then you must believe in reheating as well, because reheating takes us from the cold and empty universe at the end of inflation to the hot and thermalized universe at the beginning of nuclear synthesis. Reheating is a very interesting stage of the evolution of our universe because it has very interesting nonlinear dynamics associated with it. And as I just showed you, this nonlinear dynamics, for example, could lead to the formation of localized and long-lived objects such as oceans, which might, for example, affect baryogenesis, the generation of the asymmetry between matter and antimatter. And we also see that the nonlinear dynamics of reheating is very interesting and exciting because we can get objects such as oceans, which are normally thought of being really stable, to become unstable when coupled to other forms of matter, which is something unexpected. It's not trivial to understand. Yep, and that's it. Thank you very much for your attention.
Very nice introduction as well, and you speak right, which is great. So, if you have questions, please, we have plenty of time for the questions in this session.
Got one. Does reheating have any particular impact on the sun?
Excuse me, what?
Well, would that process of reheating have any impact on like smaller solar systems like ours?
I don't think so. Reheating is a very brief and short stage of the evolution of our universe, and it happened everywhere. So the entire universe was affected by it. And there were no solar systems and no galaxies when reheating took place. So it might have influenced the entire universe, but not particular parts of it.
And also from what you mentioned, they're unstable, so today they're not discussed exactly.
Actually, I mean, it depends on the model which you're considering. It depends on, everything is very model dependent. But oceans could be around us even today. They are actually one of the candidates for dark matter particles. Well, again, depends on the field which forms oceans. So, for example, if we're in our projects, we consider oceans formed out of the fermentation of the inflaton field. And when we consider the inflaton field, we know that the mass scales there are, well, 1 million the plant mass. So these are really massive objects, and their size, they would be of the order of, well, they will resemble elementary particles today. We won't see spatially extended objects. We will see elementary particles, and their mass will be of the order of 1 million, as we said, of the plant mass.